Hi, everybody. My name is Dr. Kimberly Arcand, and I work for NASA's Chandra X-ray Observatory at the Center for Astrophysics, Harvard and Smithsonian. And today I am Zooming to you from New England. And Karen Phillips, one of my fantastic colleagues, is with us today as well. And she is also Zooming to you from New England. So we're going to talk a little bit about Chandra today, the telescope that we both get to work for. We'll talk about how we make images. We'll talk about things like coding. And we will hopefully take a lot of your questions. If I could just ask students not to raise your hand during the Zoom while I'm doing just kind of like my intros, that would be great, just because it kind of clouds up in front of my screen. But we will be taking lots of questions later on, I promise. And at any time, you can put your questions in the chat, and Karen will be answering them as we go, or saving them for me to answer live. So let's get started. So we're hoping to have some fun today and make this really interactive. So we would like to start off by taking a poll. Karen, if you want to launch poll number one, this first question is just getting to know you a little bit. If you are given the opportunity, would you want to go into space? So go ahead and select either yes or no. And while you're doing that, I will tell you my answer is a definite no. I have absolutely no desire to go into space. I wanted to be an astronaut when I was very, very young. And my parents were super supportive of me, but I was one of those kids that got like sick on any kind of ride at the park. So even though my parents probably knew that I should not be an astronaut when I grew up, they were still very supportive of me. And eventually I realized maybe keeping my feet on the ground would be great. But it looks like everybody does indeed want to go into space, which is not a surprise. So we can go ahead, share out those answers, and then close down our first poll. But we will have more polls and more opportunities for interaction as we go through our webinar today. So a little bit about my background and where I came from. I actually started in biology. That's what I went to college for. I was really interested in things like bugs, ticks, and fleas, that kind of thing. So I was studying them under a microscope. And then I was about 3/4 of the way through college, and I realized, I don't want to look at bugs my whole life. Who knew? So I moved into computers. I started doing work on coding and using computers and computer science to be able to ask questions and answer those questions. And I really enjoyed it. And for me, that's kind of what brought me to work for NASA. NASA is a fantastic organization that is involved with all sorts of deep space missions, but also studies the Earth, works hard to launch things. You might have heard that they launched a really massive rocket overnight, for example, the Artemis mission. Lots of really cool projects going on there. But for me, coding was really, really important for making sure I could help answer and solve problems. So just a reminder, at any time, if you have some questions, you could go ahead. You can make note of things in the chat. If you have a very specific question, I would recommend you putting it in the Q&A because it'll be a little bit cleaner up there and easier for us to see. So the telescope that we work for, the Chandra X Observatory, it's a sister telescope to the Hubble Space Telescope, to the new James Webb Space Telescope, for example. But Chandra has been up in outer space since 1999. It was launched during a nighttime launch back in July of 1999 and has been operating beautifully ever since. So one of the astronauts who actually was responsible for leading the mission to take Chandra up into space, Colonel Eileen Collins, she was actually the very first woman to command a NASA space mission. And she is here with a very special message for you about her work on Chandra.
I'm Eileen Collins, commander of Space Shuttle mission STS-93. I was also the first woman to command an American space mission. On July 23, 1999, my crew deployed the Chandra X-ray Observatory. We had trained specifically for this flight for over 16 months. My crew felt personally responsible for the successful launch and deployment of Chandra. We trained heavily in simulators. We did standalone simulators with our training team, and we also did joint integrated simulations. Leading up to the launch, my crew was very confident that we were totally trained and ready to go. We weren't nervous. We were just primarily focused on doing the best job that we could. That summer, we had 2 launch delays. The first one on July 20th was due to a problem on the space shuttle. And then the second launch delay was 2 days later, and that was due to thunderstorms in the launch area. But we were happy to finally get the launch off on the third attempt, the third time that the crew had strapped in to the shuttle. People often ask me, what does it feel like to be in a space shuttle launch? It sounds like you're in a room that's on fire, as you've got the boosters and the engines burning around you in what we call a controlled explosion. There's so much shaking in first stage when you're on the solid rocket boosters that if you try to write, you would not be able to read afterwards what you wrote. We had a successful launch, and we were able to proceed with procedures to get Chandra on its way on flight day 1. So looking back, it was a perfect deployment. Our crew watched the Chandra float away. We took our final photos and our final videos. As we watched Chandra float away, it seemed like it was almost like a sailboat on a calm sea. We knew that no one would ever see the Chandra again, but that we would still feel its presence as it continued to send its data and its information to Earth for many years to come.
Wonderful. So they actually had a very challenging mission ahead of them because the Chandra Observatory was the largest thing that the space shuttle had ever launched. So it was actually a slightly more dangerous mission in case they had to abort or come back to Earth at any point and they hadn't yet sent Chandra on its way to work. It would have made it a little bit more difficult for them. So definitely a fantastic group of astronauts that were able to really make sure Chandra got up into space safely. So let's keep going. What does Chandra get to look at? Chandra gets to study things that are really hot or really energetic in our universe. Things like exploding stars, things like black holes, things like colliding galaxies. Also other things like baby stars and stellar nurseries, sometimes even planets. It's really exciting to be part of a mission that gets to study so many different things in our universe. So what kind of things do we use to study the universe? Well, we use light. And what is light? Light is just energy. There are all different kinds of light out there in the universe and here on Earth. So things like radio waves, microwaves, infrared light, visible light, ultraviolet light, all of these different types of light that we can use in order to study our universe. So we are going to take our second poll now. Karen, if you want to go ahead and launch poll number 2. We would like to know, which kinds of light have you used in your life? So have you used infrared light by any chance? Have you used or are you familiar with ultraviolet light? Have you ever used X-rays or have you ever used visible light? Now I can give you a hint that most of you have used visible light. Visible light is the type of light that humans can see with their eyes, but you probably also use some of these other kinds of light as well. So for example, if you've ever put sunscreen on your skin, that means you've protected your skin from ultraviolet light from the sun, UV light. If you've ever gone to the dentist or the doctor, if you had a cavity or if you thought maybe you had a broken bone, then your doctor or your dentist probably used X-rays to be able to shine it down onto your skin, to be able to see through your skin into your bone or into your tooth. If you've ever heated up some food in a microwave, you've used microwave light to disturb your food, the water molecules in your food, to heat it up really, really fast. And most of you probably used infrared light as well. If you have ever, for example, used a remote control to turn on a light or to turn on the television or to run a car or something like that, a toy car, you've probably used infrared light to be able to talk between that remote control and the device. So there are many different kinds of light in the universe. We'll go ahead, share out the poll, and then close it down. It looks like most people were very familiar with X-rays and visible light, and then a couple people with infrared light and ultraviolet light as well. So that is really nice to see. Thank you for participating in the poll. So why do we care about these different kinds of light? Well, I'd like you all to sort of picture in your minds, say you're going to a local baseball game or a softball game, and you sit down in your seat and perhaps you've got some popcorn and you're ready to watch the game. But when you look out onto the field, all you see is what's on my screen now. You're just seeing a little bit down that third base foul line. That's all you're seeing. Now you don't know what else is happening on the field. You don't know, is there a pitcher? Is there a catcher? Are there players on the field? Is there even a ball? all you're getting is this very tiny slice of all the available information you could learn or could know. So the equivalent here is that if we could only see our universe with the type of light that our eyes can see, which is visible light or optical light, it'd be like only being able to see just a tiny sliver of that baseball field. We'd be missing all of the other information out there about the universe. But if we can see different kinds of light, then that fills in the baseball field and gives us a much better idea of what's going on in the game. What are the rules of the game? Who's playing? Where's the ball? Did somebody score, right? So being able to study many different kinds of light is really helpful, not only for astronomers out there in the universe, but also for people down here on Earth, different kinds of scientists and different kinds of engineers. If anyone here is musical, if perhaps you play the piano, for example, you can think of a similar analogy. If we could only look at the universe in optical or visible light, it'd be like having middle C and a couple keys on either side. All the rest of your piano keyboard would be missing, right? So it's really important to have all those different kinds of light to be able to fill in those keys on your keyboard. And we'll take a look at some examples of this now. We're going to look at a galaxy. We're going to look at a galaxy, which is just a huge mass of stars and gas and dust. We live in a galaxy called the Milky Way galaxy. It's a beautiful spiral-shaped galaxy with these spiral arms that is just a wonderful place for us to be able to live. But there are other similar spiral galaxies out there in the universe, and we're going to look at one called M51, or the Whirlpool galaxy. So it's got some really lovely spiral structure to it, just like ours, but it also has a little tiny companion galaxy that's kind of hanging out with it. And so if we look at this galaxy in X-ray light, the kind of light that the Chandra Observatory gets to detect, we're seeing lots of really hot, energetic things like bright stars, exploded stars, things like black holes, bits of hot gas. It's really exciting, but you're not getting the full picture. And then if you look at it in a slightly cooler light, like ultraviolet light, now you're seeing all of the light from really hot, turbulent stars. So stars that are kind of throwing little temper tantrums, if you will. And then if you look at that same field of view in optical light, or what human eyes can detect typically, now you're starting to see all of that gas and dust in that beautiful sort of spiral shaped structure. And then if you look at that same patch of sky in infrared light, which is the cooler light, now you're kind of seeing down to almost like the bones of the galaxy. You're seeing through a lot of the dust, and you're starting to see now some younger stars, and then a lot of really interesting, cooler gas and other material. But when you add all of those different kinds of light together, you get a more complete picture of what this object looks like. So now you're seeing those bright purple spots. Those are the things like the exploded stars, things like X-ray binaries, which are just pairs of stars hanging out together, things like black holes, that kind of stuff. And that's in all that bright purple. And then you're still seeing the cooler lines of that infrared light that's showing off those sort of bones of the galaxy. You're still seeing the blues of the ultraviolet and the greens of the optical, but it's giving you a more complete picture of what it is we're trying to understand. So with that, we are going to take a break and try to answer a few questions. So Karen, do you have anything lined up for questions in the chat? Anything specific you'd like me to answer?
Oh, yes, we have a lot of great questions. Oh,
Great.
It's exciting. One that I think is exciting, and because it's just, there's so many opportunities there for you. What interests you the most about our solar system?
Oh, our solar system is a really, really good place to be, right? We're lucky enough to live again in that Milky Way galaxy, but we live out on a corner of one of those spiral arms in our very own solar system, where we have our wonderful sun, our very own star, and we have that smattering of planets that orbit around our star. Now, because of where we are in our galaxy, it's a pretty cool, chill place to be. So I think what's very interesting about our solar system is just all the differences among those different planets that we have, right? If you think of like Mercury, for example, it's just one side is super hot and the other side is super cold. You can think of Venus, and Venus kind of gives us this glimpse of like what happens when there's sort of out of control climate change, if you will, causing all of these really hot greenhouse gas kind of problems. Then you can look at Earth, which is of course my most favorite planet, of course, because it's where we live. And then you can look at Mars, which feels like it should have been perhaps a nice planet to live on, but yet it has a sort of wimpy, weak atmosphere and is really not super habitable at all. Not somewhere I'd actually want to live. And then we get to the big ones. So we've got Jupiter, we've got Saturn, we've got Uranus, it's just amazing all the difference between those different gas giants and ice giants and all of the different things you can learn about them, as well as the moons that are orbiting them. So I guess my short answer is just how different all of those planets are from each other. I think it's pretty cool.
Oh, great. So our next question is from Matthew, and he would like to know, what is your favorite nebula or galaxy?
Oh, well, that's really hard. There are billions and billions and billions of them out there. But I was playing the Cat's Eye Nebula earlier, right before we started the field trip, if you will, and playing the sound from that information, that data. And that is probably one of my favorites. I love any kind of planetary nebula, which is what the Cat's Eye Nebula is. It's called a planetary nebula because back in the day, before we had advanced telescopes, researchers thought that they might have been planets because they sort of had fuzzy telescopes that made them look like blobs. But we now know they're not anything really to do with planets. They are essentially stars like our sun that have started to age, that are sort of running out of their fuel a bit. They're starting to puff off their outer layers of those stars. And what happens when they do that is it causes these beautiful sort of circular or other kinds of concentric shapes around that star. And I think it's really interesting because it gives us a glimpse of what our own sun might do in perhaps, say, 5 billion years. That's billion with a B. So that is a huge amount of time. We are totally safe for the short term. Our sun will, by the way, never explode, but it will eventually turn into a planetary nebula in about 5 billion years or so. But I think we'll hopefully by then figured out an evacuation plan because 5 billion years is a really, really long time.
Then we have another question. It's
Mhm.
interesting. It says, do you know what the biggest star is, or does that even really exist? Like the biggest star?
Oh, the biggest star. That is a good question. I actually feel like I know this, and I can't think of what the answer is. But so I should say there are billions and billions of stars in the Milky Way galaxy alone, and there are billions and billions of galaxies. So we can't say what the biggest star in existence is because we don't know all of those stars. That math, that number of total stars in the universe is, well, astronomically high. It's so big. We can't even like count that high. But we can talk about what astronomers have observed with our various satellites and telescopes. And I believe there is one, it might be called like Stevenson something. It's a red or a hyper red supergiant star. I don't remember what the full name is, but I know it's got Stevenson in it. So if you want to look that up, I'm sure you could find out what the numbers are. It's probably like 2-23 or something like that. And that is known to be a really, really, really large star. So our sun, in comparison, is actually kind of small in comparison to that, very small. Our star is kind of an average size star, average age star. It's in the middle of its life, which makes it sound kind of boring, maybe. But of course, it's not because our star has quite literally meant the world to us. We wouldn't be here without our star, without all of that wonderful light coming to Earth, just the right kind of light coming to Earth, the wrong kinds of light being blocked by our Earth's atmosphere. And it's really wonderful star for us. But in all, our Earth is really kind of puny in comparison with some of these super giants. So yeah.
Okay, great.
Time for
Then
one or two
from
more?
Ari, yes,
Great.
we have plenty. From Ariana, what's the most fascinating thing you've learned about space?
Oh, that's a great question, Ariana, and also kind of tough because in astronomy, there's so much to know, and there's so much that we don't know. So I know a very tiny, tiny bit of the total information that's out there. Like it's such a tiny, tiny fraction. And I kind of like not knowing things. I like thinking how much that there is to learn out there. So trying to like pick one thing that I know and like the most is challenging because every day I'm learning something new. Every day I'm learning tons and tons more about stars, galaxies, black holes, and all the rest around us. But I guess maybe I would talk about my favorite object, which are called exploded stars, also known as supernova remnants. Those type of objects are much more massive than our sun, the stars. Before they explode, they're at least 8 times the size of our sun. And for context, you could fit like a million Earths in our sun, right? So our sun is already big to us, but not that huge in general. And our sun can explode, but stars that are more massive than our sun can. And when they explode, they just explode their guts out all over the universe. And those guts, they're made up of iron and silicon and calcium and sulfur and neon and all different kinds of chemical goodness. And that material, that stuff, just kind of moves out into the universe and is swept up into new generations of stars, of planets, of potentially people, right? So quite literally, we are star stuff. You have, iron in your blood and calcium in your bones. And those materials have most likely come from stars that exploded their guts out all over the place many, 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 many years ago. So that's one of my fun facts.
Great. So next question is from Melanie. And this is about the Chandra satellite. She'd like to know, how far can it see?
Oh, great. So Chandra can go really far. Chandra is what's called a high resolution spacecraft. So it can see things around a black hole pretty much just before it passes the event horizon, just before it passes that point of no return. It's seen some incredibly distant galaxies and distant black holes. It peered into a patch of the sky, a really small patch of the sky, and found thousands of black holes. So it can see back about 13 billion years or so, which is pretty incredible and very exciting to be able to get that kind of information, to be able to study it and to turn it into images or sounds or other things. So yeah, these have been great questions. Should we resume the talk, Karen, or do you think we have time for one more?
We have time for one more.
Great.
What is inside a black hole, and where do you go if you go in a black hole? That's always this is a very popular question.
Yes, and black holes are fantastic objects to think about and to talk about. So a black hole is a really, really compact object. They're often formed when, say, a really, really massive star, again, way more massive than our sun, when that star runs out of fuel, it collapses in on itself and then explodes all over the place. And during that explosion, it's so tremendous, it's so cataclysmic, right? So much is happening that sometimes a black hole can form, which is this super, super compact object where nothing, not even light, can escape from it. And so there is a point around that black hole where that gravitational pull is essentially so strong that you can't even see anything around it, right? Because light can't escape. So what that means is they're really hard to study because you're studying for something that is essentially invisible, like you're trying to find kind of like that needle in a haystack, if you will. So what scientists have to do is they have to study the things around the black hole. So if they think a black hole might be somewhere, it's because they're seeing stars around it act a little strange. Like they might look like they're orbiting something, but nothing's there. And if that's happening, that means that there's probably something like a black hole there that they just can't see. And so you probably have seen, or maybe you haven't seen, some of the very first images of a black hole. Now, what does an image of a black hole mean? Because we can't actually see a black hole. What those first images of black holes were is they're essentially like the shadow of a black hole. Or if you've ever painted a silhouette, where you cast a light onto somebody so that there's a shadow that's being cast onto, say, a wall or something like that. And then you can sort of draw or chase that silhouette and do a painting of that person, say, from the side. That is the kind of idea here with that black hole image. And that first time we were able to see that, we were seeing that sort of silhouette, which I think is really, really cool. So, all right, why don't we get back into the talk? I know not everybody can hang on for the full hour, so I want to make sure everybody's comfortable and gets to see as much as possible. But thank you so much for the questions. Please do continue to drop them into the Q&A at any time so that we can sort of figure out what it is that you would like to know more of. And so At this point, I'd like to launch our next poll. Karen, if you want to launch, I think it's poll number 3. And that is, what is binary code used for? Have you ever heard of binary code? If so, do you think binary code is used for talking to computers? Do you think it's something that is used for talking to dogs? Do you think binary code might be something you use to send a message in a bottle? Or do you think that binary code is used for talking to a toaster? Go ahead and put in your answers. And I believe in this one, you can select more than one. I will just say that as we're waiting for answers to come in, binary code is essentially a simple language or a simple way of sharing information between one electronic device to another. So you can use binary code, for example, to be able to talk to a smartphone. You can use binary code to be able to talk to something like a smart fridge. If your refrigerator has a little computer in it, then binary code could be used to talk to a smart fridge. But we do indeed use binary code to be able to talk to our spacecraft like Chandra, like Hubble, like the Webb Space Telescope, in order to be able to tell them to do things. So the answers, if Karen wants to select and show what everybody has put in for, it looks like most of you selected talking to computers, which is absolutely correct. Some of you put talking to a toaster, which is correct, because if you have a smart toaster with a computer chip in it, you could indeed talk to that toaster. And a couple of you put in, or one person put in talking to dogs, which if you've ever seen the movie Up, is definitely something that would be cool. But as far as we know, I don't think we can yet talk to dogs through a computer chip, but it might be coming, so you never know. All right, so that was a fun bit of trivia. So let's talk a little bit more about how we get data. How do we get this information of our universe? How do we get the information like the image behind me in my background, right? So we have incredibly interesting telescopes like the Chandra Observatory or the Hubble Space Telescope that are out there looking at things in outer space. So Chandra is just named after a famous Indian American scientist and astrophysicist whose full name was Subramanian Chandrasekhar, but his nickname was Chandra. And Chandra also happens to mean moon in Sanskrit, which I think is pretty cool. Chandra is about the size of a school bus. It's about 14 meters, so it's pretty big. And as I mentioned, it was actually the biggest thing to be shoved into the space shuttle and sent up into space. So Chandra goes about a third of the way to the moon on its orbit around Earth. That places it in a kind of highly elliptical orbit, and it has taken over 3,000 trips around our planet since it was launched back in 1999. So that means Chandra overall has traveled 3 billion kilometers. It's captured 25 trillion bytes of information or data, and it has taken scientists and engineers and computer folks 4 million lines of computer code to be able to tell Chandra what to do. Because since Chandra goes a third of the way to the moon, the way that we talk to it is through that binary code. The way we talk to it is by sending up different commands through computer science to be able to tell it what to look at when. So we are going to take a brief tour of a behind the scenes look at what the Chandra Observatory Control Center is like. So we have just come off the elevator of the Chandra Operations Control Center. This is the place where everybody essentially has to take care of Chandra. If Chandra has to go to the doctor, if you will, we have to do that from our control center down here on Earth and send up the commands that will fix Chandra and take it to the doctor. So right down here in this hallway, this is one of the main halls, and there's a little exhibit on the left that talks about how Chandra was built. So if you want to learn more about Chandra, how it was built, how long it took, please feel free to come back into this tour at any time. It's publicly available, and Karen will drop it into the chat. So this is the main control room, and this is where a bunch of scientists and engineers will sit to be able to make sure Chandra is operating well and doing what it needs to do. So there are some lead spacecraft folk that sit in these desks, and over here is another engineer that takes care of essentially making sure the right commands are sent up to our spacecraft. Then we've got some more banks of computers where we have additional engineers sitting to make sure that all of the little subsystems, all of the individual parts on Chandra are working well and working beautifully. And then up here in this front row, that is where all the science instruments engineers and other scientist folks sit. And they're the ones that kind of make sure that the way we get the data from that information from the universe to Chandra, that those pieces are all working. And then finally up here in the front of the room is this massive wall of monitors. And those monitors are really important because this is kind of like all the medical data of our telescope, right? So up here on this main screen, you can see a bunch of green boxes. Those green boxes are telling you that things are a-okay with Chandra. If any of those boxes go red, then that's going to tell you that there's something wrong. So at any time, if you're an engineer sitting in this room, you might get an alert that one of those boxes has switched to red, and that means there might be an issue that you have to figure out. And how they're going to figure that out, they're going to have to figure out what the problem is. If it's perhaps the telescope's temperature is too high, right? Just like humans can get fevers. Well, in a way, a telescope can get a fever too, because it's out there in outer space. And so it's dealing with all of that radiation from our sun. And our sun is wonderful for us because we have Earth's protective atmosphere. But without Earth's protective atmosphere, you have to be very, very careful because you don't want to overheat. Just like a human doesn't want to have a fever, a space telescope doesn't want to have one either. So temperature control is really important. And that would be one of those boxes, one of those little data points, if you will, that they would know that Chandra is operating well. It also shows us where Chandra is in its orbit, that highly elliptical orbit, that sort of oval shaped orbit around Earth. It tells us where it is in its orbit at any time. It shows us what Chandra is looking at out in the universe. And it also shows us when it's downloading data. So what happens is every 8 hours, the telescope talks to one of NASA's Deep Space Network dishes, and it sends all of the information that it's been collecting over 8 hours, like a full work day, if you will, down to the NASA Deep Space Network dish. And then eventually that makes its way to our laptops here in Massachusetts. And so that's a really great way for us to know what Chandra's up to when we can collect all that data and see what it's observed and what it's taken its captured information of. So all of these screens are really important for helping us understand how healthy our spacecraft is and if it's doing what it needs to do. And so anytime you want to come back into this virtual control room chat and tour, you can go ahead. I just want to show you one more thing over here in the corner. We've got some of our engineers made a little drawing of some of them holding up the Chandra spacecraft with the text, "Keep it up, Chandra Ops." So that means, keep Chandra up in space, and Chandra Ops is Chandra operations. So I'm not a very great artist, so I'm always impressed by this, but maybe you all would like to draw something yourselves and how it relates to Chandra. So I think we will stop sharing here. I will just say there's plenty of other rooms that you can check out if you do want to do this tour on your own. For example, there's a place where scientists and engineers get to sleep, because we have some bad weather up here occasionally in New England, like blizzards and hurricanes that we can get. And there have to be people taking care of Chandra and watching over Chandra at all times, even during the pandemic, when things were very sort of scary and we didn't know what was going on. Having people in the control room remains really important. And so they just put in a lot of safety measures and made sure everybody stayed safe, and still were able to keep Chandra operating and running. So that was the control center tour. I'd like to take you just essentially to see a few of my favorite sites out there in the universe. I mentioned earlier some of the different kinds of things we get to look out in space, and this is one of my favorite as well. This is essentially a stellar nursery. There are these tall columns of gas and dust where baby stars are forming inside, and that's kind of all it is. All of the bright spots you're seeing around it are stars that have already formed. So this is a kind of like what's called a stellar nursery. You can think of like a baby nursery at the hospital, say, right? This is a star nursery instead, where all those young stars are kind of hanging out together as they grow. And new stars are waiting to be born. This is one of my favorite images. This is an area just off the Carina Nebula, which I have behind me. And I think someone actually already identified correctly in the chat earlier, which is impressive. Again, this is an area where stars are forming, and there's lots of teenage stars here, and they're having kind of like these bright temper tantrums. And that's all that bright pinkish purple color that you're seeing. And then there's all of this like slightly cooler gas and dust that are hiding newborn stars and young stars in general. We also get to look at just individual stars or even pairs of stars. So this is our Aquarii, and this is essentially a pair of stars that are dancing together. And as they're dancing together, they're kind of sending out this additional energy, and that's what's causing this really beautiful, almost like a bird-like structure. I don't know if anybody here sees the bird like I do, but I feel like it's a pretty strong looking bird. It's quite lovely. And also galaxies, those collections of billions of stars, of gas and dust, all in this case, a nice, really lovely spiral shape in the one in the bottom, and a slightly less spirally shape, but still flattened pancake-like shape on the one on the top. And groups of galaxies. This is another relatively popular image from the James Webb Space Telescope that also has data from Chandra. So it's got X-ray and infrared light, and we're seeing essentially like 4 galaxies hanging out together. And as they get too close to each other, there's kind of like some extra excitement that happens, because some of these galaxies are eventually going to merge, and that causes a bit of excitement around it. And you see that excitement in that bright blue color. And then finally, we have clusters of galaxies. So this is essentially hundreds of galaxies that are all grouped together. And it kind of looks like a smiley face just because of the positions of some of those brighter galaxies, and also because of what's called gravitational lensing, or the bending of light that makes it look like what we call the Cheshire cat cluster of galaxies. So those are just some of my favorite sights to see. Again, how we capture all this information. There's this light that is out there in the universe, and it's been traveling towards us. And so a telescope like Chandra is pointed at that object. It captures the information, it packages it up into binary code and sends it down to Earth. And then we've got this binary code, we've got this digital suitcase of information. We have to unpack it and figure out what to do with it. So coding is really, really important to astronomy because we use it pretty much everywhere. So we're going to take our next poll. I think this is poll 4. Yeah, I believe this is poll 4. Karen, if you want to go ahead and launch it. So we want to know, just for fun, have you ever been an astronaut or some other kind of NASA space related costume for Halloween? So go ahead and let us know if you have, and you've got a cool costume that you've been. You can pop that in the chat. And we'd love to hear what you've been. I've seen people go as shuttles. I've seen people go as astronauts. I've seen people go as the James Webb Space Telescope or the Hubble Space Telescope. I've definitely seen all kinds of really interesting space themed costumes for Halloween. But it looks like most of you are saying not yet, but maybe you'll get a cool idea for the future. All right, so thanks for taking that fun poll. And let's go ahead, share it out, and then move on. So as we mentioned, this idea of binary code, these digital suitcases are really important because that's how we talk to telescopes in space. It's also how we talk to things like smartphones, to laptops, to any kind of smart computer-based device. And it's just a system of ones and zeros. You can think of it like if you want to send a friend of yours a secret message, you encode it in a special way that the two of you can understand. It's the same thing here. So we just use this system of ones and zeros to be able to talk to different machines and get that really cool information of our telescope. And now we talked earlier, once we have that binary code, we unpack that digital suitcase and we can make stuff. And some of the things we get to make are images, like I've been showing you today. And we can use all different kinds of light to make those images. This is one of my very favorite objects in the universe called Cassiopeia A, and it is a beautiful exploded star in the Milky Way galaxy. It's about 10,000 light years away from us, where a light year is the distance that light travels in 1 year. And that's about 10 trillion kilometers, which is a pretty big number. So we can look at this patch of sky with the Hubble Space Telescope and see this beautiful wispy structure. And then we can look at the same patch of sky in X-ray light, and now we're getting all this superheated debris, things like the iron, the calcium, the silicon, the sulfur. And now we're seeing all of that, debris, that stellar vomit, if you will, that is slowly moving out through the universe. And all of this that we're looking at is because of that binary code, all of that coding and software that we used. We can also use more coding and more software to create three-dimensional models of these things and 3D print them. So you can hold a dead star in your hand, for example, and we can turn them into sound. So at the very beginning of this talk, I played a few pieces of what it sounds like when you take this information and you translate it into sound. So this is what this exploded star sounds like when you do that translation. Now, this is not like holding up a microphone to the sky. This is taking the data and just translating it into something you can hear. And here we go. I really enjoy doing this kind of work with sonification, particularly because I tend to work with people who are blind or low vision, some of my colleagues and friends that are blind or low vision, for example. And it's a really great way for people who are blind or low vision to be able to work with data of the universe and understand the data of the universe in that way. So there's one more piece I'd like to play. This is the sonification or translation of that information into sound of a black hole. And this is what that sounds like. This is another piece we worked on this year. So in this case, which is interesting, is there's this really super massive black hole in this cluster of galaxies, right? And there's all this hot gas around that black hole. And that black hole is sort of sending out energy, and that energy is disturbing the hot gas and causing what's called a pressure wave, which turns into a sound wave. So in this case, there are actually sound waves that this black hole is kind of singing out, and we can use math to figure out what the note of that sound is that that black hole is singing. And it's kind of cool because scientists figured out that it's B flat, but it's about 57 octaves below middle C, which means it's hundreds of piano keyboards south of what humans can hear. Many, many, many times lower than anything humans could ever hear. So what we do is we're not hearing these sounds directly, we're translating the information into something we can hear, which I think is pretty cool. So if you're interested in learning more about how we make sounds and how we use coding to do it, we have a new hour of code activity out this year called NASA's Space Jam. It's suitable for grades 2 and up. And you can find that at chandra.si.edu/sound/code. And it essentially lets you build your own solar system and then pluck the strings of it like you might pluck a harp or a guitar in order to make your own sounds. And it's pretty fun. You learn a little bit of coding with blocks, and then you also learn a little bit on the sonification and then a little bit about planets as well. So we hope you'll enjoy that. So I think at this point, Karen, I will pass it over to you to lead us in a little binary code activity.
Yes. First,
Great.
I would like to start off with taking a pretty cool poll. I think poll number 5. That would be, have you ever tried coding? Yes or not yet?
We've got a lot of yeses
great
so
answers
far.
here.
Yes.
Seems like most people have. That's
Wow.
great.
Amazing.
Good intro. Okay.
And it looks like some of the students are commenting that they've coded in HTML and JavaScript.
Yes.
Wonderful. Wonderful to see that.
Kim previously mentioned that binary code is the format in which we talk to machines. And that leads us into a fun binary code activity that we can do now. This chart that you see shows English language alphabet characters corresponding to 1s and 0s. In this activity, you'll write your capitalized initial in binary code. There is a binary code chart for lowercase letters as well today, but we'll use the capital chart for this activity. So for example, my initials are KP. So I would write for K 01001011. Then for the P, I would write 01010000. You can share your binary code initials with your teacher or pop it into our chat. And in the meantime, Kim is going to continue taking questions.
Wonderful.
And I'll leave this up here while you guys do your initials.
Great. All right. So it seems like there's still quite a lot of activity in the chat, which is wonderful.
Right.
Looks
So
like
a good question we have from Xavier is, what is Saturn's ring made of?
Oh, that's a lovely question. So Saturn's ring is made up of a whole lot of little stuff, like little bits of rock and little bits of dust and little bits of like ice. And it's gravitationally held, so that pull from the planet is binding it essentially in that orbit around it to make those really gorgeous ring structures. There are some larger bits of debris in those rings as well, but for the most part, it's made up of relatively small stuff considering the size of that planet, which is pretty massive. So yeah, that's a great question. There's a lot of really cool objects in our solar system. Should I go into the Q&A section for questions?
Well, we have another question that's quite popular that
great.
we
Okay.
always get.
And?
The very popular, what happens after a star dies?
Oh, yes, yes. So as I mentioned, not all stars can explode. So it really depends on the size of the star, right? So the size of the star determines its fate, right? If a star is really kind of small, and I think I saw a question in the chat earlier on what was the smallest star. Well, typically the smallest stars are called brown dwarfs. Some people like to think of them as failed stars almost because they're quite dim, perhaps not super exciting, are kind of, just there. But I actually think brown dwarfs are really interesting because they are so small and they don't really waste much energy. They can live for a really, really long time. So they kind of just keep on keeping on. We think they can live to be about 55 billion years, perhaps in some cases. That's billion with a B. That is a huge amount of time. The entire universe is only 14 billion years-ish. So living 55 billion years is very, very long. So I like to think of those brown dwarfs as interesting because they get to see so much of the universe in a way. And then there are stars like our sun that we talked a little bit all about already. They're kind of medium-sized star. Our sun is at the middle point of its age, but eventually it will puff off its outer layers and turn into that planetary nebula. And after it's done with the sort of expansion and the puffing off, the core of our sun will be left behind and it'll be very small and much denser than it is now. And then there are the massive stars. The massive stars are sort of those big party stars in the universe. Really, the more massive that star is, the shorter its life. And so a star that is very, very massive, like some of those massive stars that other people were asking about, when they run out of fuel, their core collapses and they explode their guts out all over the universe. And that can be it. Some of the most massive stars, after that explosion, there could be literally nothing left. They could be just obliterated. And all that's happening is that stellar gook is just going out into outer space. For slightly less massive stars, so still really big, but not the most massive, a black hole can typically form at certain points. And then slightly less massive than that, something called a neutron star can form, which is essentially a really, really super dense, bright core where like a teaspoon of that material is worth, I don't know, it probably would weigh like a million elephants or maybe even many millions of elements in one teaspoon of material. That's how densely packed it is. So it really, the fate of a star really does depend on its mass. So there's no one answer that what happens when the star dies, because stars can die in different ways. And each one is kind of like a choose your own adventure, which is interesting because if you know the size of that star and you know its approximate age, you can kind of get a roadmap for what will happen with it. So
From
go ahead. Yeah.
From Mosin, he'd like to know, can Chandra take pictures of the sun?
No, great question though. So Chandra can't take any image of the sun. Chandra has taken images of Earth. There is definitely a couple observations of Earth. Chandra's been able to look at our moon. Chandra has been able to look at Mars, Venus, pretty much all the planets, I think, except Mercury. But can't look at the sun because the sun is so bright and Chandra's instruments are so sensitive, it would just burn and ruin them essentially. So Chandra has something built onto it called a sunshade. It's kind of like a large baseball hat flap, if you will. And that is always tilted in the right direction to make sure no sunlight is getting into the front of Chandra's telescope. And also, scientists pay very particular attention to make sure Chandra's never pointed anywhere near directly at the sun. So Chandra typically is aimed away to make sure that, again, it stays as safe as possible, because that sunlight would essentially just fry Chandra to a crisp. And that would be really too bad. And Karen and I would be out of jobs, and that would make us sad. So we don't want that.
It's a lot of questions for black holes today. Did we answer this one? Someone says they are having if you can settle something between them and their brother. Their brother says when a black hole dies, it turns into a white hole. Is that true?
So that is not true that I'm aware of, but I will be completely honest. And I mentioned earlier that I know a very small amount of information about our universe, and I'm comfortable not knowing. And there are definitely areas of things with physics once we get into like deep cosmology, multiple universes, and wormholes. Those are the areas that I'm like, that's not anything I'm comfortable talking about. However, from what I understand, it's not exactly like a path from a black hole to a white hole. However, I say that, and also I should say that there's so much scientists don't know about black holes, right? In some ways, black holes seem sort of very elegantly simple, but in another way, they seem almost unknowable. And so we can't know exactly what happens inside a black hole, because nothing can ever escape once it goes inside a black hole, mostly, right? Even at the process of how things fall into a black hole, for example, are fascinating. It's called spaghettification. Quite literally, as an object approaches a black hole, and that gravitational pull from that black hole gets stronger and stronger and stronger. Eventually, you'll be locked in that embrace of the black hole, essentially. And once that happens, very sort of slowly, you'll just be pulled into thin molecular spaghetti, because that gravitational tug is that strong. I don't think a human could ever survive that. And of course, we can't send spacecraft that far. So all we can do right now is watch things like stars get eaten up by a black hole. If a black hole's having a smaller snack, it might eat like an asteroid, right? And we'll see the flares as that's happening. But otherwise, there's a lot that we still need to figure out about black holes, which I think is pretty exciting and pretty cool. And that means that if any of you are interested in becoming astronomers, there are so many questions available to answer, that plenty of jobs for pretty much everyone here on the chat, and then some. Any other cool questions to answer? We've got about 5 minutes left.
Let's see. Well, we have a lot. Let's see. Well, we have some things like how big is Mars? How big is Earth?
I see a question.
If the Earth stops spinning?
Oh, well, it wouldn't be good. As far as I know, if the Earth stopped spinning fast, I don't think we'd be stuck on the planet very long. We'd go flying off of it. So that wouldn't be good. I do see a question in here. How long have you been working for NASA? That I'd like to answer. Just because it's really cool getting to work for NASA. The NASA mission that Kira and I both work for has, as I mentioned, been operating since 1999. And I started actually working for Chandra in 1998. So I've been here almost 25 years. I think it'll be 25 years in May. And Karen, you've been here a while too. How many years are you at now?
Probably the same.
Pretty close, right? Yeah,
close.
Not too far behind. So yeah, Karen and I really like working for Chandra. Awesome.
Yeah. Oh, so did we have another question? Mm-hmm. Did the Chandra take off in 1999 and then keep landing, or did it do it in one big trip?
Okay, so yeah, what happens is the space shuttle with the astronauts on board was launched into outer space, carrying Chandra in its belly, essentially. And they brought it up to a like lower Earth orbit, so kind of hugged close near Earth. And it opened up the sort of belly of the space shuttle, and an arm deployed Chandra and sent it off on its way to work. And so what happened is, once that arm pushed Chandra out of the belly of the spacecraft, the space shuttle, Chandra had a little booster on it, like a little extra engine, if you will. And that extra engine had a little motor that kind of pushed it up into its orbit that it's currently in now. And so it has been operating up in that orbit ever since. So again, like 23 or 24 years by now, Chandra's been operating, going a third of the way to the moon, and has never come back home. So it will never visit us again. Once we said goodbye to it back in 1999, that was it. We'll never get to touch it or like see it physically with our own eyes pretty much again. Interestingly enough, Chandra was only supposed to last for about 5 years, but there's nothing on Chandra that runs out of fuel, for example. It is powered by the sun. It has solar panels, and there's nothing expendable, what it's called, so nothing that Chandra will run out of. So as long as Chandra continues to be healthy, meaning it's not getting whacked by any meteoroids or anything like that up there, it'll continue to be able to do its job. Eventually, it might have problems with that fever that I told you about. It can get overheated in a way. And there are actually some things under discussion to be able to figure out, maybe we could send a robotic mission to fix Chandra at some point, who knows? But at this point, Chandra will hopefully reach 25 years, coming pretty soon, and hopefully get to stay studying that hot universe for even longer than that. So yeah, that's a really great question. We've only got 2 minutes left, so maybe one quick, simple one, if there's a simple question.
Okay. If you could go to all the planets, which one would you go to?
Oh, okay.
If you could go to one, just go to one.
Just one. All right. I think I'd have to go for one of the gas giants. So I would love to go to Saturn because of its rings, but I think I'd have to say Jupiter. I would really love to like get a little bit up close and personal with that great red spot, although not too close because it's like a hurricane kind of system, if you will. And of course, because Jupiter does not have the real like cool, crusty, physical core that the Earth has, we'd have to be visiting Jupiter with like balloons. And we'd have to be careful because there's definitely a lot of pressure on that planet. And so it would be an adventure to be sure. But I guess I'd have to go with Jupiter. That's a great question. And I think what's really cool about planets in general is that, our own solar system is awesome. But there are so many other planets out there that we're learning about. Planets where it rains glass sideways, where it rains rubies or diamonds, zombie worlds around zombie stars, water worlds, lava worlds, pretty much anything you can cook up in your imagination. And scientists have found a similar planet to it. So they're really looking hard to find planets that are like Earth, to find planets that, might have some like really good water, that might be perhaps habitable. Lots of mysteries to figure out with planets. So yeah, keep thinking about those planets. I think that's a great question. So, all right, we are at the hour. So I think we're going to stop here. These were tremendous questions. And I know we did not get to all that many of them, but we tried. I actually enjoyed seeing the busy chat. It was really nice to see that energy here. I hope everyone got to enjoy our first ever elementary school special virtual field trip. And Karen, thanks so much for joining us today.
Thank you.
It was really lovely to be here. Bye-bye.
Thank you.